Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to discuss about an application of dynamic programming, which is nothing but a transitive closure, which can be found using Warshall'S algorithm. Now here we are going to see what is transitive closure and how Warshall'S algorithm can be used to find the transitive closure. So here you can see what is transitive closure. So given a directed graph, find out if a vertex j is reachable from another vertex I for all vertex pairs I comma j in a given graph. So here this Warshall'S algorithm is used to find out if a vertex j is reachable from another vertex I for all pairs of vertices in the graph or not. So here what is meant by reachability? Reachability means there is a path from vertex I to j. So no need of having a direct edge. If there is a path from I to j, then we can say that the vertex I is reachable from vertex j. So that reachability matrix is called as transitive closure. That transitive closure can be found using Warshall'S algorithm. So here you can see this example graph. So here we have the graph with 4 vertices, which is a directed graph. Now here the transitive closure of this graph is represented as like this. Now how we represented? Actually, what is the adjacency matrix for this? The adjacency matrix for this graph is written as like below what we have. So here 0 to 0, there is no since self path, it is going to be represented as 0. 0 to 1, there is an edge, it is going to be represented as 1. 0 to 2, it is 1. 0 to 3, there is no edge, so its value becomes 0. 1 to 0, its value is 0. 1 to 1 is 0. 1 to 2 is 1. And 1 to 3 is also 0. And 2 to 0. So here I have 2 to 0 a path, so that's why its value is 1. And 2 to 1. 2 to 1 is not there, so it is 0. We have only 1 to 2, but there is no 2 to 1. And 2 to 2 is 0. And 2 to 3 is 1. So here I have the path, so, edge. That's why it is 1. 3 to 0, it is 0. 3 to 1 is 0. 3 to 2 is 0. And 3 to 3 is also 0. So this is to be called as adjacency matrix. That is, if there is an edge, then its value becomes 1. Otherwise, its value becomes 0. Right? But adjacency matrix is different from transitive matrix. In case of transitive closure, if there is a path, we represent its value as 1. Otherwise, its value as 0. So here you can see how there is a path from 0 to 0. Actually, there is no edge from 0 to 0. Its value is 0. How there is a path from 0 to 0? I can reach from 0 to 1 and 1 to 2 and from 2 to 1. This is a path from 0 to 0. Right? So that is to be called as a path is exist, so that's why we can write its value as 1. Right? Now in the same way, here you can see, here there is no edge from 0 to 3, but in transitive closure, there is a path from 0 to 3. What is the path from 0 to 3? Here I can move 0 to 1, 1 to 2, and 2 to 3. This is the path from 0 to 3. Like that, we can represent all those values. So that is to be called as transitive closure. Now, how this transitive closure can be calculated? Here I given one more example for the transitive closure. Here, this is the adjacency matrix and this is the transitive closure. Here you can see the difference of adjacency matrix. There is no edge from A to A. There is no edge from A to C. There is no edge from A to D. A to A is edge is not present. A to C edge is not present. A to D also not present. Right, all these values are 0 in case of adjacency matrix. But coming to here, A to A, there is a path. Even there is no edge, there is a path. What is the path? This is the path from A to A. In the same way, A to C. This is the path from A to C. Now, A to D. Here, this is the path from A to D. Right? So we have path from A to A, A to C, A to D. So that's why these values are changed to 1, 1, 1. So like that, we can write the path matrix. That path matrix itself is to be called as transitive closure. Right? Now, how we can use Warshall'S algorithm for finding the path matrix. So here, this is the simple representation of Warshall'S algorithm's logic for finding the path matrix. Now, what is that logic means? So here, this always represents logical and right. Now, here, the value of the transitive closure at a stage k, the value of Rk of ij, and the element ij value in the stage k of Warshall'S algorithm is represented with either this element or this element, either this element or this element. That is, if this value is 1, the value of this also becomes 1 directly. If this value is 0, in this case, this value is equal to this value. So that is what it is representing means here I, j are 2 vertices. Okay, so if I am taking the transitive closure matrix for I comma j, so if there is an edge from I to j, then its value becomes directly 1, right? In that case, in the next level also, its value is lies as 1 only. Since there is an edge, its value is lies only. That is, in the next phase means R1 of I comma j. In this case, this value also becomes 1. If there is no edge here, so here there is no edge. So here I and j vertices are present, but there is no edge. In this case, here my R0 becomes 0. R0 of ij becomes 0. In this case, I need to find whether there is a path from I to j via k. K is another vertex. If I have a path from I to k and k to j, then I can reach I to j. That's why in this case, this value becomes 1. Right? The same thing is explained here. So in Rk minus 1 of I comma j, if the element is 1, then Rk element is also becomes 1. If the element is 0 in Rk minus 1, in this case, we check whether from I to k and k to j is possible or not. If it is possible, its value becomes 1. Otherwise, its value becomes 0. That is, there is no edge as well as there is no path also. Right? Now, let us see an example how we can solve the problem. Right? Here you can see the same explanation. So here I have Rk of I comma j. Right? So I want to find this value Rk of I comma j. How it becomes 1? Initially in Rk minus 1, its value is 0. Right? Now, how its value can be updated? Let us see. If Rk minus 1 of I comma j is equal to 0, if Rk minus 1 of I comma j is equal to 0, in this case, what this value becomes? Rk of I comma j, what this value becomes? This one, right? What is this one? Let us see. Rk minus 1 of Ik. What is Ik value? 1. And Rk minus 1 of Kj. Rk minus 1 of Kj is also 1. 1 and 1 is nothing but 1. So Rk of Ij value becomes 1. Like that, we go for updating the values. Right. Now here we are going to see an example. Now for this, what the example we have taken earlier, the same example I am going to explain. Right. Now here you can see that this is a given directed graph and it's adjacency matrix. So here this is to be called as adjacency matrix. Right? Here this is adjacency matrix. Initially R0 becomes the adjacency matrix. Right? After that, I want to find R1. Right? How to find R1 using this R0. Now let us see. In case of R1, which values may be updated means these values, the values which are present in first row and first column. Right? This is 0th column, first column, second column, third column, 0th row, first row, second row, third. Right? So the first column and first row. R1 means first column, first row. These values can be updated. Right? Now, how these values can be updated? Let us see. Now here, we can see that how this value can be updated. R1 of B comma A, R1 of B comma A, whose value is, I need to find, right? Now, how it can be find? If R0 of B comma A is 1, its value becomes directly 1. Let us check this one. R0 of B comma A is 0. It is not 1. So that's why I need to use this formula. R0 of, here now I am finding R1. Here my K is equal to 1. Right? Rk minus 1 means R0. R0 of I comma J is 0 here. Right? Here my I is B and my J is A. Right? Now here Rk of B comma A is 0. Right? So this formula can be used. Now let us see by using this formula what it becomes. R0 of, what is I? I is my B, comma, what is K here? K means 1. What is the one element here? One element is again B only. Here my 0th node is A, first node is B, second node is C, third node is D, right? So one node means B only, right? And R0 of, now here what is my K? K is B only. And what is my J? J is A. Now R0 of B comma B is 0 and R0 of B comma A, which is 0. So this value becomes 0 only. So here it is 0 only. Now we will see here when I solve all these values will not be changed, but this value will be changed. How this value is going to be changed? Let us see how it is changing. R1 of, what is this one? B comma B. This value I want to found. Right. For this, first I need to check R0 of D comma B. What is R0 of D comma B? It is 0. So this formula I need to use. Now in this formula, what are these values? Let us see. R0 of I comma K. Here what is my I? My I is B. And what is my K here? K is 1. 1 means, which is nothing but B. 1 means B. And right, sorry. I said you D means B means 1. 1 node means A. Right. I'm going to find like this. 1 node means A, B, C. Fourth node means D. Right. I'm going to find up to, this is R1. This is R2. Here I am going to find R3. Here I am going to find R4. So that's why here 1 means A, D to A and R0 of, here K means A and my J means B, A comma B. Now let us see. D to A. Here I'm going to find D to B, right? D to B directly there is no H. Now I am checking that via 1 it is possible or not. Here 1 is nothing but A. That is via A it is not possible or not, I am checking. Now R0 of D to A. What is R0 of D to A? 1. And what is R0 of A to B? R0 of A to B is also 1. 1 and 1 which becomes 1. So this value becomes 1. So here it will be updated as like this. Now we check only first row and first column when I am going for R1. Now if you see R2, in this I am going to change second row and second column. That is, this is 0, 1, 2, 3. This is 0, 1, 2, 3. Here this is the second row and this is the second column. That is what is this meaning means. What it means here 1 means A, 2 means B. So here I am going to find B is my via vertex. When I am taking 1, A is my via vertex. Whether it is possible or not, through A I am finding. Here B I am taking. Whether it is possible or not, B I am taking for finding that one. Now let us see here. these values can be found, right? So when I am considering these two, here you can see these values are updated. These values are updated. Here you can see A to D and D to D can be updated. Via B, I can solve these two, right? There is a path from A to B, B to D. Initially, there is no path from A to B, right? So here, there is a path. In the same way, D to D also. I can go from D to B and I can go from B to D again. There is a path. So here in this way, I can move, right? So this value is also be updated. So like that, we go for finding R3, R4. Finally, we will get at R4, we will get the transitive closure of given graph. Right. Now, what is my given graph? Let us see what is the transitive closure of whether this becomes the transitive closure or not. So this is my given graph. Right. Now, check that whether it is the transitive closure or not. So here check this. So here check this. Whether there is a path from A to A. Yes. Here I have path from A to A. This is the path from A to A. Is there a path from A to B? Yes, there is a direct edge. Is there a path from A to C? Now, what is the path from A to C? So here, this is the path from A to C. Now, A to D. Here, there is no path, direct path from A to D. Now, what is the path from A to D? Here, this is the path from A to D. So that's why these values are updated. Right? Here also you can see B to A, B to A. So, what is the path from B to A? B to D and D to A. Right, B to B, B to D and D to A and A to B, I can move, right? In the same way, B to C. So I have a path from B to C like this, right? B to D. Here there is a direct edge from B to D, right? Like that, we will find entire transitive closure. That transitive closure always represents the path matrix. Whether there is a path from a vertex I to J, whether there is a vertex path from whether there is a path from the vertices I to J, that can be found by using this transitive closure, right? Now, I hope that you all understood how to calculate the transitive closure. Try to solve one more problem, then you can clearly understood. Thank you for listening.